Welcome to learning module number 6, where we will study corrosion. I am excited that we got to this part, which is the major component of this course, as you may guess from the title. All right. Corrosion is extremely important. It is, as an engineer, perhaps there is a set of skills that you would like to have. And first is to spot the corrosion. Second, perhaps what is a lot more important, and that is to be able to predict that a certain environment that is created anywhere in the plant, in the process, or things like that, or even in the house, you may predict that a certain corrosion, and at the end of this course, you will even identify what kind of corrosion may occur under certain environment. And perhaps as an engineer, you always want to be a step ahead of corrosion. You never want to find yourself in the scenario that the corrosion was happening while you were not able to either detect it, predict it, or measure it. Now, making a statement that corrosion is important is not enough to motivate you to study corrosion. So perhaps I'm going to rely on history to help me demonstrate what happens when corrosion goes unnoticed. Today, as part of the introduction, I would like to tell you about the Aloha airline Boeing 337. This is an event that took place in 1988. So just to visualize for you what exactly happened, on the left picture, you see the plane as it just landed. So you can clearly see that decompression occurred and a major portion of the plane was gone. And you can see that happened while people were on board, and most importantly, people were actually 24,000 feet above the sky, right? And then this is just an image of what actually the plane looked like after they evacuated people. You can see that this is, well, it's either business class or first class. It doesn't matter the difference, but let's actually take a moment to understand what exactly happens in this particular scenario. So the plane takes off and it gains an elevation, a very typical elevation, which is about 7 kilometers or 24,000 feet above the land. And at that point, what happens is that the plane experiences a sudden decompression. So in a sense, it's almost like the portion of the plane just got exploded, right? It's not because there's an explosive, but because there's a pressure gradient, right? So the higher up we go, the lower pressure is up there, right? And so if all of a sudden you have a certain portion in the plane that doesn't have the original integrity that is designed for this pressure gradient, what happens is that a certain portion of the plane gets sucked in by the vacuum. That's exactly what it feels like, right? Because the pressure inside the plane is higher than the pressure outside of the plane, right? Due to the elevation. Now, but why that happened? So the panels, the plane at that point has been in service for quite a bit. However, this should not have happened if they saw that corrosion was happening. And that was going a little bit, the corrosion was happening undetected. And they used, in this specific plane, they used aluminum alloy where the panels were on top of each other, right? When they are, and they were also fixed with a rivet. This was the design. And the idea is that that specific structure, right, the riveted portion and the underneath, the portion underneath where they had the panels started corroding. So corrosion in general, that means it's a deterioration of your metal. So you may start with something that is very strong, that is something that is reliable, but all of a sudden if the material deteriorates with time due to corrosion, it loses its strength, it loses the integrity. And so when the flight was up in the air and due to the pressure gradient, what happened is that the cabin just lost those panels and a sudden decompression happened. Was it avoidable? Absolutely. How? By inspection, right? Because corrosion is something, for the most part, is something that you can visualize. Sometimes not with a naked eye. Sometimes you do know you need to know a specific corrosion knowledge that allows you to actually predict and suspect the corrosion that might happen within the material, while on the surface the material still looks shiny and still looks strong and fine, right? And that's what you guys will actually be able to do by the end of this course. Now, the reason it is a tragedy is that the skills of the both pilots, the captain and the pilot, they still allowed to land the plane, and all of the passengers were able to arrive safely, except the stewardess who was serving one of the seats in this front row. Let's call it a business class, either first class, doesn't really matter. But she was the only person who was not fixed, right? And when the sudden decompression happened, basically she got pulled out of the airplane, right? Not to give you any phobias, but perhaps maybe after knowing that this can happen whenever you are in the airplane, I do highly recommend you to wear your seatbelt just for the scenarios like that. Because if anything happens, you can be sucked out basically into vacuum, right? And this is why we're wearing a seatbelt in the airplane. And perhaps you should wear the seatbelt all the time without even pilot asking you to do so during the turbulence. Now, and during this course, and as part of one of your projects, you will look into more cases like that, and you will realize that typically when the corrosion goes undetected, when people do not inspect it in timely manner, when they do not do the correct predictions, usually when the accident happens, it is a major tragedy that usually takes a lot of lives away. And for that reason, corrosion training should be mandatory for any engineer that goes out there and works. And perhaps from this moment on, you will notice that the knowledge that you will be gaining within this course, especially the knowledge related to the corrosion, this is not something that is relevant just to pass this course. This is something that you would like to pile up in your brain and actually take it to the field, because you will notice how helpful it's going to be, the things that we cover within this course. All right, now the purpose of this video is to introduce the corrosion and explain it in depth. I really want you to understand every single part about what happens within the material when the material corrodes. And then once we grasp that concept, then we start building on top of it, a layer by layer. Okay, so as I said before, corrosion is a deterioration of a metal resulting from chemical attack by its environment. Okay, and one of the ways, the chemical attack here, in a sense, is a key word. I have the exact same definition on the prior slide as well. Chemical attack here is a key word, because we can look at the corrosion just as a basic, simple chemical reaction. Okay, and if you can assume that corrosion is a chemical reaction, right, that means that the rate of corrosion depends upon temperature. And so hopefully you remember it from the Arrhenius equation, right? And it will also depend on the concentration of reactants and products. And this comes just from the basic knowledge of chemistry, right? If corrosion is actually a chemical reaction, right, then I can control it. I can manipulate it by manipulating the temperature and the concentration of reactants and products. Right now, what happens is that whenever we talk about corrosion, we often refer to metals, and this is important to understand. You may occasionally hear that people may say, well, ceramics and polymers corrode too, and perhaps this would be not the proper way to use the word corrosion. When it comes down to ceramics and polymers, the right way to express the corrosion there, we should say degradation, because the concept there is a bit different from the metallic corrosion. The reason metals corrode is, for now, what I'm about to say may not make any sense, but by the end of this course, it will make a lot of sense. We already know something about the metals, is that metals have a lot of free electrons, right? And that is, it's a major advantage for certain applications, such as the whenever you need to conduct either electricity or the heat, right? There's nothing better than metal, right? It's the best choice for you. But in terms of corrosion, having these free metals becomes a major disadvantage because these free electrons, they set up electrochemical cells within the metal structure. And whenever you have this electrochemical cell, now if that doesn't ring a bell, that's okay. I'm about to break it down. Very, very simple. But by the end of this lecture, what you should be able to explain to yourself and explain to anyone is what electrochemical cell is. Because once you know what that is, you'll be on the lookout for electrochemical cell because you'll know that's how the corrosion kicks in. That is how it develops, and that's what you need to avoid whenever you design or build or construct anything. Um, Now, metals also have a tendency to go back to low energy state by corroding, and that's in reality is true. If you take any pure metal and if you leave it out in the air, it will corrode. Why? Because when it happens, when corrosion occurs, metal actually goes to a lower energy level, and we've discussed that even when we brought up the bonding. Everything in nature tends to exist in a lower energy state. And I give you an example, at some point, a very simple example as a human being, right? If you have an opportunity to stand on both feet, you'll do so. You're not going to stand on one foot because it requires more energy. If somebody offers you a chair, you'll use a chair. And at some point, laying on a couch would be even more preferred, right? Because it allows you to actually preserve your energy, right? And that happens to everything, every living object in the world, beginning with electron, right? Electron, atom, molecule, and so on and so forth. Everything tends to exist in a lower energy state. Okay, well, because earlier I did say that corrosion is actually a chemical reaction, right? That means that I can break it down, right? And usually you can break it down into oxidation and reduction, okay? And I would like you to visualize the experiment. I do not have a video, but I figured that we can just use our imagination and it's going to be very simply to visualize. Let's corrode our first metal. And I would like you to corrode zinc. So I'm zooming in on this image to explain what exactly is going to happen. You don't see zinc anymore, right? But you see a path of zinc actually falling into the vial. So I have a vial with hydrochloric acid in it, okay? And I'm gonna take a tiny, tiny target of pure zinc and I'm gonna drop it in there. And what you will see is that all of a sudden, you will see vigorous bubbling. Your target is gonna be just basically dissolving, right? The material is just gonna be disintegrating and you will see a bunch of bubbling going from the solution upward, right? And that's what the image actually captures. Now, there's a way to actually write down this equation, and this is going to be your pure zinc plus hydrochloric acid, and you end up with the salt, zinc chloride, and the hydrogen gas that you see as bubbling. And later on in this course, you also get to corrode iron. And if you do so in acidic environment, you will also be able to see the bubbling, and that's exactly what the same scenario as here with hydrogen. Okay, but this is not enough. I would like to draw what exactly happens to the zinc as I'm dropping it in hydrochloric acid, okay? Because this is a reaction, right? I just gave you the reaction, but I want you to break it down to understand exactly what happens to the zinc. Now, how do I produce hydrogen, okay? And perhaps that would be a good idea to start drawing it with me. It's a very simple sketch. So I'm gonna have this metallic zinc. Think of it as a small bar, okay? And I'm gonna introduce it to the hydrochloric acid. So I have a bunch of this H plus, and then yours know that the sizes are off, right? The sizes are off. But because we know that hydrogen is the tiniest guy, right? But it's okay. I'm not really taking into consideration the size, okay? Now I'm looking at the metallic zinc that is in the pool of hydrochloric acid, which will have hydrogen atoms and chlorine atoms. All right. I have to, one of my pets is trying to get into my office. My apologies. I'll be back in 10 seconds. Let's first look at what exactly happens to zinc. So I'm going to draw this one zinc atom right here, okay? Now, as we mentioned before, is that metals have free electrons. So what exactly is happening to zinc here is that zinc is going to donate two electrons. Okay, there's electron one, and perhaps to make sure you can see it, I'm going to switch the color. There's going to be electron 1 and electron 2, right? It just goes by the valence. But that means that your zinc right here is not as neutral atom anymore, right? This is now zinc 2 plus, okay? And then there's going to be consequences of that. Now that you're looking at the ion, right, specifically a cation, it will now get dissolved in the electrolyte, which is your hydrochloric acid. So that means is that you're gonna have a floating zinc 2 plus in here, right? And this is how you will see the dissolution. And that means in this space right here, there's going to be an empty space, right? Basically, it's going to be losing the integrity, right? And of course, I'm just like zooming it in. But what actually happens is that you're losing a little bit of your material, right? Now, what happens with the electrons that got released by the atom, right? Well, these hydrogens gonna travel toward the surface, and then what's gonna happen is that each will actually accept the electron, right? And now they become, if each H plus accepts an electron, you end up with now neutral hydrogen atom, and now we have two. These two gonna combine and they're gonna produce a molecule which is gonna be your gas, right? It's gonna be your hydrogen gas, and this is the bubbles that you see leaving the surface, okay? So if I am to now, let's break it down, and now let's actually write down it reaction-wise. So once again, what happens to the zinc? From neutral atom, you go to a cation that and these free electrons, right? The electrons are picked up by the hydrogen ions, and this produces hydrogen gas that bubbles in the solution, right? And that's why you will see something like this, right? We're basically looking at the dissolution of zinc and the formation of hydrogen. Now, this reaction here, the first reaction is called oxidation reaction, right? This is oxidation of zinc. This is called reduction, right? Reduction. And this is why any corrosion reaction, right? Any corrosion process can be described by oxidation reduction reaction, right? And you will actually be able to write it down for any corrosion process. Now, one more thing to keep in mind is that this region right here, I'll use the green color, this region right here where you have the dissolution of zinc, right? This is going to be your anode, okay? And I will discuss more about this later in today's video. The spot, this local spot where the oxidation happens or the corrosion happens, right? This is what we call anodic region, right? Or a local anode. And now the area where you have the formation of hydrogen, right? I'm going to put it here. This is your local cathode, okay? So at this point, before moving on with me, it is paramount that you understand these two half reactions, right? Oxidation and reduction. Okay, so once I drop my zinc into hydrochloric acid, the zinc, right, the neutral zinc actually produces, loses electrons, right, and forms these positively charged cations. And this is how zinc leaks into the electrolyte, right? Basically, leaving holes in the material, and over time what would actually happen is that I have a zinc leaving space here and here and here and here, right? And so eventually what happens is that my material basically just disintegrates, right? And I'm just showing you steps of what it happens, but over time I'm losing more and more material, and visually, right, what I'm drawing here, it's more of a microscopic vision, right? But what you actually see is the bar just basically disintegrating in front of your eyes. Okay? So, as I just described, is that on top right here, you can see the full reaction, right? Where you have zinc plus hydrochloric acid, and you produce salt, and you have the formation of hydrogen gas, right? But most importantly here is that I want you to recognize the oxidation reaction and the reduction reaction, because oxidation reaction is where corrosion takes place, right? This is going to be your reduction reaction. So once again, to summarize oxidation reaction, this is where you have metal ions forming, right? And that happens at local anode. Now the reduction reaction, right, where you have the reduction of metal, this will be happening at the cathode. One thing to keep in mind is that both oxidation and reduction reaction take place at the same rate, okay? And later on, you will find out how helpful it is, because oxidation is where corrosion occurs. But I can either control that reaction or I can control my reduction reaction, right? If I control my reduction reaction, then this is the same way I control my oxidation reaction. Later on, you will see how, as engineers, we use that knowledge to actually control the reaction happening. Okay, now if we are, so the example we looked at is zinc. And it explains you the concept of how metal corrodes, and that concept is going to be the same for all metals. Just the number of electrons that are released will change depending on which metal you look at. However, is that all metals have a different tendency to corrode. Okay, and you probably know it because I will give you an example. Whenever you're trying to purchase a jewelry, right, you do not wish to buy anything from copper, right, or nickel or other materials, because you know that you want to go with something that doesn't corrode, and those metals are the noble metals, right, such as silver, gold, platinum, right, and they are alloys. Meaning that some materials corrode and have a high tendency to corrode, example, aluminum, versus some metals, even though they still have these free electrons, but they have a lower tendency to corrode. So the question is, as an engineer, well, but how do I rank the metal? Is there a way to rank all metals in terms of their tendency to corrode? And if there is a way to do so, how would I accomplish it experimentally? Now, there is a way to do so. There is a method that allows you to compare the tendency of metals to corrode. And then what we do is that we actually compare the half cell oxidation or reduction potentials, and we do so with respect to the hydrogen half cell potential. Now, instead of just explaining what I'm looking at, I'm going to draw this exact same diagram on a separate slide, because, and I want you to start drawing it with me. Of course, I won't be able to replicate the way it is here, but I'm sure I can do it well enough. I'll grab it and I'll drop it in the I'll insert it here. So in a sense that we will have it somewhere on the bottom of a slide, and I will just explain you before I start drawing. So in this particular example, we will still consider zinc, and you guys will notice what happening here is that I basically have my zinc, and then my zinc is connected to my hydrogen electrode. But it's not actually a hydrogen electrode, it's actually a platinum electrode, okay? So let me draw it step by step, and I do encourage you to draw the same thing with me. So to measure the tendency of any metal to corrode, I'm going to do the following. And keep in mind is that this bar that it's a target bar, right? It could be out of any metal, right? So this is the thing that you will be swapping depending on which experiment you're running. Zinc, aluminum, magnesium, and things like that. To begin with, I'm going to start with zinc because I already know what happens with zinc when zinc corrodes, right? Now, you will also need another electrode. You want to use an electrode that doesn't corrode, right? And this is going to be your platinum. And the reason you want to achieve that is because I would like to connect these two electrically through an electric wire. And in between, I will be able to, once the circuit is closed, right, meaning that the electrical current can go through it, I can actually measure the voltage. And that number, it's going to be unique for every single metal. So if I am to replace zinc with magnesium, I'm going to have a completely different number. But that's the number I'm going to read the moment I flip the switch. Now, there's going to be a little bit more. In here, I'm going to have an aqueous solution of zinc chloride, right? So that means that I will have a bunch of zinc 2 plus, right, floating in here, and I will have a bunch of chlorine minus, right? I don't know if you can see the minus. And once again, this is an aqueous solution. And I will have a platinum electrode, and the platinum electrode is going to be in the hydrochloric acid, again, aqueous solution, right? Meaning that I have a bunch of this hydrogen plus, and I have a bunch of this chlorine minus, okay? So hopefully now we understand what is floating in the solution that surrounds my bar, right? Now I'm going to explain the concept step by step, and please follow the concept with me. I know that zinc has free electrons, right? And then what's going to happen is that these free electrons, if I have this zinc atom, right, I'll draw it as I should draw it. Well, this is my zinc atom, right? And this zinc is going to release two electrons. These two electrons, we just go by valence, right? If it was silver, it would be just one electron, right? But because the metal has these free electrons, now I know that I connected my zinc to the other metal through the wire, right? Through another metallic wire, meaning that I have a channel for the electrons to flow. And these electrons will actually flow. They will flow this way. They will arrive all the way to the platinum electrode, and keep in mind, platinum electrode here does not corrode. Platinum electrode here is solely, purely as a conductor, right? So platinum doesn't corrode. It's a conductor. It allows us to actually lead our electrons all the way to the hydrochloric acid. Now, when these electrons arrive here, let's say I'm going to put it right here, you have electron here and electron here. They're going to be at the surface of the platinum electrode, right? I know that it's inside the hydrochloric acid, and so that means these hydrogen ions that are readily available in the solution is going to come up here, and I already know that they're going to form a hydrogen, right? Well, perhaps first there's going to be hydrogen neutral atoms, just as alone with the previous example, and then two together is going to form the hydrogen molecule, and then this is what you will observe as gas, right? Now, that process, right? Once you flip the switch, meaning that it's think of it like a shutter. Once I remove the shutter, the electrons will flow just because there's a potential differential. And then in here, you will see the number, right? That number will allow you to describe the tendency of material to corrode. And what happens is that this is what scientists came up with. And we need to keep in mind is that in every single experiment, they capped this reaction, right, at the hydrogen. Oh, perhaps I will repeat it again, the reaction itself, right? This reaction right here, where you have H plus electron, right, gives you hydrogen gas. This is going to be my reference point. So I'm going to assume that this is the zero. And in every experiment, I'm just changing my metal on the left. I go from zinc to aluminum to potassium and so on and so forth. But for this specific example, I will have my zinc that actually dissolves into ions, right, and releases electrons, 2 electrons, okay? So on the left-hand side, I'm actually looking at my oxidation reaction, right? And on the right-hand side, you have your reduction reaction. So if I am to look at this table, keep in mind is that this guy right here, and perhaps I shall highlight it like this, you will notice that it is assigned to be a zero, right? This is your hydrogen reduction reaction, right? This is your reference for all metals. And then you will notice that some of the metals ended up above, such as, for example, silver, right, or copper or tin. Some of the metals ended up above the reference point, and some of the metals, such as nickel, cadmium, zinc, aluminum, magnesium, lithium, these materials, they ended up below the zero. And here's what happens. The more positive, this number that you see on the voltmeter, right, less tendency to corrode. The more positive this, the standard, and we call it, perhaps I shall say, the standard electrode half cell potential, right? That's the number you see on the voltmeter. And it turns out is that the more positive it is, the less tendency to corrode. And then the more negative that number is, the higher tendency to corrode. And in other words, I can also describe it now that I know the difference between anode and cathode, right? Anode is where corrosion happens, right? The material basically also means more anodic, going downward, right, from that zero. The more negative, the more anodic material has a higher tendency to corrode. And here we're going to describe these metals as more cathodic, okay? And so, and once again, in this experiment, oh, perhaps I forgot one more thing. And if you guys will notice that you will have a charge buildup, I will do explain what happens here. Since you will have, and I'm gonna draw it here, what is happening as the process goes on, you will have a bunch of zinc 2 plus populating your solution, right? And you know that these are positively charged, so you're kind of like bringing more and more of this positively charged zinc, and in a sense, you're building this positive charge in one solvent, right? And then on the other hand side, you are consuming your positively charged hydrogen ions, and that means now you depleted the hydrogen ions, and that means you have more and more of this chlorine negatively charged ions, in a sense that now I have this charge buildup. And not to interfere with your experiment, you don't want to build the charge on one side or the other, right? You're also going to introduce some salt. We call it a salt bridge. It's usually looked like a glass tube, and inside the tube, we introduce ions that just fall into the solution to, so as this charge buildup happens, I forgot the word, to neutralize it, right? So I'm bringing this salt, and that means that if in this side, you will probably introduce either sodium or potassium, and in here, you will actually introduce your chlorine negative and potassium positive, right? because they will be falling out as into the solution as needed, mostly to just neutralize your solution and keep it what it was at the to begin with, right? It's just in case if you start looking in depth into this picture right here, and you will notice that it does have a salt bridge, and this is why we need that salt bridge there. Okay. So now, just to summarize everything I've said so far, now this, the potential of voltage, right? And we also label it as E naught, right? Of the metal is directly measured against a hydrogen half cell electrode, right? Meaning that the reaction that you measure, you compare each metal to this reaction, right? Where you have two H plus two electrons, and this gives you hydrogen gas. That is my reference, and I assign it as 0. I just assume that is going to be my 0, and then the number that I see on my voltmeter is going to actually allow me to rank the metals as more cathodic or anodic, right? And the rule is the more positive E naught, right? That means the easier for the substance in the reaction to be reduced, right? Or in other words, it means that the less tendency to corrode this material has. The more negative E naught, the easier for the substance in the reaction to be oxidized, meaning that it has a higher tendency to corrode, right? So, and right in here, I'm using more simple words for you. If a metal is anodic to hydrogen, right, that means that it has more tendency to corrode. Anodic, that means it has to be below our reference point, right? It has to be less than 0. And here's an example. Iron and sodium. So let me go up here, and I would like to identify this too. I'm going to use a different color, perhaps red. Here's your potassium, right? And sodium, my apologies. You will notice that it has a very, very negative potential, right? Minus 2.71. That means it has a high, very high tendency to corrode. And then another example was iron, and specifically iron 2 plus. And that's the typical iron you see everywhere, that rusty color that you see, that's the iron that we are referring to here. One thing to keep in mind is that there are two irons in this table, and eventually if you look, and I actually want you to look through the entire table and to familiarize yourself with the metals that are displayed here, you will notice that there is another iron right here, okay? And it actually has a positive potential, 0.77. But you will notice that the difference here is that at the bottom you have iron 2 plus, and on top you have iron 3 plus. Typically, by definition, whenever I am giving you problems, and if I do not specify the valence, we go with iron 2 plus. If for some reason, and there are certain examples, when I do specify that you're working with iron 3, that means that you will be looking into this table and you will be working with iron 3 plus, right? The one that has 3 electrons. All right, but so hopefully it all makes sense. To summarize this entire slide, now my hydrogen reduction reaction is my standard, is my reference, right? I assume it's 0. Now, if I measure the tendency, if I measure the potential on the metal, and if it is above my hydrogen reduction reaction, that material has a less tendency to corrode, right? It means more cathodic. Anything below is going to be more anodic. And if I am to compare, let's say in here, so hopefully you guys understand, if I am to compare, let's say aluminum, or perhaps I'm going to stick with the ones that I have highlighted, iron and sodium, right? Which one has a higher tendency to corrode? Sodium, because it is more negative, right? So I can also compare metals in this specific table, and we'll come to that too. All right, and so meaning that I will finish my thought since it is on this slide. If a metal is cathodic to hydrogen, it means it has a less tendency to corrode. An example is going to be gold and copper, and that shouldn't come as a surprise that yes, the metals such as noble metals, right? Gold and the silver are all of the ones that you can actually see. Well, I see a silver. I don't see a gold. Perhaps they just don't have it on this specific table. I see the silver, positive 0.8. I don't see the gold unless I'm not attentive enough. Yep, I don't see it here. but both of these metals, you will see them on top, right? Because those are noble metals, and this is why they don't corrode or have a very low tendency to corrode. Now, earlier we did mention something about galvanic cells, right? Electrochemical cells. How does it work and where it happens? In reality, when I set up this picture for you, it may not actually be very helpful because as an engineer, you're thinking like, well, I don't actually set up anything like that in my process. That's not what I work with when I work with unit operations and things like that, right? So I typically have either a single metal that I work with and that metal corrodes, right? Or I actually most commonly have two metals connecting with each other. And that's where the danger comes from, right? Because in here, now that we know that every metal has a different tendency to corrode, whenever you connect metals, and you would be surprised how often you have to do it. If you own a boat, right? Let's say a boat is made out of aluminum, and all of a sudden you need to put some rivets in, right? That's a metal touching another metal. If you are in your bathroom, if you go into your bathroom, you'll see a lot of connections, right? And that's several metals connecting to each other. And it takes knowledge, engineering knowledge, to make sure that you connect pieces uh, that that you're not setting up a galvanic cell, right? What is a galvanic cell? Let me explain what exactly the galvanic cell and how it works. And to explain you what the galvanic cell is, how it works, and how the corrosion kicks in, I'm going to use this diagram right here. Okay. And I'm going to go a bit faster because I think at this point I'm going to insert it right here. And first we're going to look at what we are looking at here. Okay, so the only difference from the previous figure I showed you is that you will notice that now I don't have this platinum electrode, right? I actually have two metals, and one is zinc and another one is copper. And these two are connected through the wire. And the question is, will they corrode? If they corrode, which one will corrode? And if it does corrode, how it corrodes and what happens to another metal, right? So, since I have zinc and copper, let's connect these two first. Okay, so I have a zinc, and I'm gonna connect it to the copper. I'm going to connect it through the electrical wire. And that is, guys, important because if I am to remove the electrical wire, what I'm about to describe won't be happening. You have each metal corrode on their own, and it's going to be a bit different. I'm trying to set up a galvanic cell. I'm trying to replicate an example of a real life problems where you have one metal connected to the other one, right? And especially when those metals are made out of have different compositions, right? But later on, you'll find out that even making them same composition sometimes doesn't resolve the problem, okay? So now I'm going to put them into this solution, and it's going to have like a semi-permeable membrane because I will have here 1 mole of zinc 2 plus. And then here I will have 1 mole of copper. I'll have a cuprate and copper sulfate. So that means I have a bunch of this SO4 2 minus floating everywhere in the solution, right? And the reason the membrane is semi-permeable, at some point you will notice that I will also be creating a scenario where one of the metals leaks into the electrolyte, meaning that it's going to build a positive charge. And so once we find out which metal it is, you will notice that this SO4 is going to travel that way, right? To go there and to stabilize it, neutralize it, because I'm setting it up in terms of an experiment. Okay, so zinc and copper. First thing that we want to know is that we're going to find these two metals on the standard electrode half cell potential table, right? I'm going to switch to the blue color. And first, I'm using the zinc color. My zinc has the standard electrode half cell potential of negative 0.76. Okay, negative 0.76. Got it. My other material is copper and it has a positive potential of 0.34. Right away, as an engineer, this should be a red flag. This should be like, oh wow, this is danger because I am literally taking two materials, right, that have a different tendency to corrode. And the moment I partner them together, I'm going to set up a perfect experiment, a perfect electrochemical reaction where one of the materials will be corroding and will be corroding fast. Okay? What does that mean? That means that zinc is going to lose your electrons, right? And if it loses electrons, you have a bunch of zinc that is leaking into the system, right? And what we mean by that is that you have disintegration, right? So as time goes by, within this electrolyte, my zinc gets thin and thin, right? It's like the target just disintegrates and you can probably see it. And the way it occurs is that it's going to have zinc goes to zinc 2 plus and releases these electrons. The electrons continue traveling right through the circuit, assuming that the circuit is open. And once they arrive to copper, right, copper is another beautiful conductor. It's going to conduct your uh, electricity, right? Now, what's going to happen here? Before we had hydrogen, right? Hydrogen comes up, consumes the electrons, and forms hydrogen gas. Well, this time it's a bit different. Guess what? This copper right here is gonna come up and it's gonna, because it's copper 2 plus, and it can actually accept those two electrons and it becomes copper, right? It's a neutral copper. And what happens is that you have a material that's now going to be attaching you all this available copper, right? All this copper 2 plus now can travel, right? Accept the electrons, and now it's going to electroplate on the material. So as the time goes by, this bar is going to be very super thick, right? Should I just realized that it's better that I change the color so you guys understand how the shape will change. So as the time goes by, what happens is that on the left-hand side, I have my zinc corroding and corroding really fast. Corroding. I was trying to say that my zinc being an anode is corroding, right? Kind of sandwich those two. So zinc is corroding and it is corroding pretty fast, whereas copper is actually electroplating. Now, and I know that right now you're looking at the example and you're probably thinking like, okay, so what's the problem? The problem, if I have a plate and if I use the wrong bolt, and if I put this bolt in and all of a sudden these two are different. One is um, cathode, another one is anode, regardless of which one is, right? You don't want any materials to corrode. Now, the first rain happens where moisture is trapped in between. Here's your electrolyte. These two are now in your intimate contact, right? So electrons will be floating. So all of a sudden, as an engineer, you were asked to fasten something. You came there without a single thought, without knowing about the galvanic cell. You set up a beautiful galvanic cell. They're going to call you later and they'll tell you that the entire construction collapsed because of you, right? Because the anode, whatever it is going to disintegrate and it will disintegrate fast. And you will be surprised. Well, plumbers usually know a lot about corrosion. They just know that you don't set up things like that. Often either by training or sometimes by just learning by experience, right? Connecting, fastening wrong materials, and then later on finding out that these materials, one, and the way you always see it is that one is fully corroded and another one is just going to be look like as is, right? But this explains you what the corrosion is, and this is one of the most common corrosion that happens in real time. And later on, I will show you that not you don't have to have two electrodes. This process can happen on one electrode, right? On one. And actually, why I would say later on, I'll show you. This is exact same process when it happens on zinc, right? The only difference is that I don't have two separate electrodes. I actually have one zinc, one bar, but on that bar, I have a local anode and I have a local cathode. right? But in the end, if I am to create the environment where I can have my electrons passed through into the electrolyte, right? I have material disintegrating, and while whatever the side effect of it, right? In this particular scenario, you only see the generation of hydrogen, right? But if I am to go back into my galvanic cell here, which is the concept of the galvanic cell, what you see here is that you actually see electroplating. Um, of course, engineers took advantage of it whenever you buy jewelry, and sometimes it says sterling silver with copper electroplated. How do they electroplate it? Just like that. This is you set up a galvanic cell, and it allows you. I know that what the layer I've drawn doesn't look nice and beautiful, but usually you can do the estimates. You can run the estimates, so you can create a beautiful thin layer. But also, my advice: does it ever make sense to buy something that is electroplated? No, because that layer is a few nanometers at most, if you're very lucky, and meaning that any friction removes that layer. So it is actually not a protective layer, and you might as well get whatever is underneath and just learn how to protect the material that you purchased, right? So hopefully this makes sense. And again, while I'm explaining things, it may make sense or may not. If it does make sense, you probably want to take time to marinate a little bit the knowledge that I just shared with you. But if you feel like, yeah, everything makes sense, I understand what happens to zinc, why zinc corrodes, where the anode is, I understand why copper electroplates here back on top. I understand why copper electroplates while zinc dissolves. I understand that they have a different tendency. I want you to take a moment and to actually draw the same sketch and explain it to yourself or explain it to to someone. That would be extremely useful because the better you understand this concept, the easier it's going to be for you further in the course where we have to identify whether corrosion is going to happen or not, whether and if it happens, where exactly, right, on which side, on which electrode. And this is actually the knowledge, typical knowledge you will be using with a real time case studies. And perhaps before I finish this video, let me give you a taste of at least one problem, right? Which shall be actually somewhat, well, let's see how it goes. Okay, so we're given the following. Oh, hold on. I feel like I forgot to, yeah, I forgot to say one more thing. Um, So whenever we have this galvanic cell, right, the last thing that you can do is that, and of course, it's you measure this potential, right? And in here you see that the number is positive 1.1. Now, how do you estimate that, right? Well, first we call it the overall cell reaction or the potential of the cell. And the equation is always the following. It's always the potential of the cathode minus potential of the anode. And so if I am to stick to the example I had, that means that my cell potential, right, is going to be E of cathode. It's always like this, minus E of anode. And that means as an engineer, I am supposed to identify, okay, which one is a cathode, which one is an anode, right? We already know, follow the flow of your electrons, right? Okay, the electrons are flowing toward the copper. That means my zinc is the anodic. Now, the potential on the copper was, I believe it was 0.34 volt. Now minus, and the anode copper has the potential of negative 0.76, right? And that means that you will have 0.34 minus 0.76, which gives us plus 0.76, and this is how you end up with 1.1 volt, right? And this is going to be the potential of the cell, okay? That's the one thing that you would need to know about the math regarding the galvanic cell. Be prepared. Sometimes I can either ask you to estimate the potential of the cell, or I can perhaps give you the potential of the cell and then ask you to figure out which metal is the cathode, given that the anode was something like that, right? So the question, it's a very easy math question, but as long as you don't flip these, right? Because of course, if you flip them and if you do potential of anode minus potential of cathode, the number will be completely different, right? So please make sure that you memorize or have it on your equation sheet, the equation itself. Now let's consider a galvanic cell where we have an electrode of zinc in a 1 mole of zinc sulfide solution. And then I have another electrode, which is nickel, in 1 mole of nickel sulfide. Okay. The two electrodes are separated by a porous wall so that mixing of the solution is prevented, right? Whenever you have a porous wall, usually it's designed to allow something to pass through, something necessary, but the mixing of solutions doesn't happen. You have pure solutions on either side. Now, an external wire with a switch connects the two electrodes. That is an important part of the galvanic cell. And hopefully now you guys think that, okay, what do I need for galvanic cell? Well, I need two electrodes, right? I need anode and cathode. I need them to be in intimate contact, right? Either touching each other or they need to be connected by an electric wire. And then fourth is going to be the electrolyte, right? I need this for the macroscopic galvanic cell to occur, okay? Now, when the switch is just closed, question number 1, at which electrode does oxidation occur? Okay, so I have zinc and nickel. Now, let me go uh, up here. Let's switch to, I already used up red. Let's switch to yellow, okay? So first I'm gonna find the zinc for you, and the zinc is highlighted with blue. So I'm gonna use the blue again. So I'm using this zinc, and the potential is negative 0.76. Now I need to find nickel. Nickel is negative 0.26. Okay, 76, 26. Let's not forget those two numbers because we will need them in a second. I'm highlighting it in blue. Now, going back to the question, at which electrode does oxidation occur? Pause the video, answer the question, then compare your answer to mine. The answer would be zinc, right? Why? Well, because zinc is more anodic, right? Even though both have a negative potential compared to the hydrogen reduction reaction, right? I just know that zinc is more negative. It's negative 0.76 versus negative 0.26 with nickel, right? Now, which electrode is the anode of the cell? What's going to be zinc again, right? Because that's the one where the oxidation, right? So oxidation and anode is kind of like keyword synonym words here, right? Which electron corrodes? It's almost all the same question, right? So perhaps these three, oxidation happens at the anode, which corrodes, right? Oxidation, anode, corrodes, same thing. Now, the final question is, what is the EMF, and that is the total potential of this galvanic cell when the switch is just closed? And I know that now you're probably thinking, like, why she keeps saying just closed? Just closed, right? Later on, we'll find out that there is a difference when you let the corrosion continue, right? We'll get there. But for now, just keep in mind is that once you close the switch, that's when we take the number, right? Well, that means that the potential, the total potential of the cell is going to be E, cathode minus anode. And I'm going to write it again, just so you keep seeing it, the exact same equation, so you know that you're not going to make mistake, right? Okay, now the cathode here, we know it's nickel, and the potential was negative 0.26. Part of me wants to go back to the equation and make sure that I'm not messing it up. Now, the zinc was negative 0.76, right? So it's going to be plus 0.76, and that would give me positive 0.5 volt, right? So this is what you would actually see on the voltmeter. All right, now at this step, we're gonna finish this video and we will continue in the next.